Welcome back, guys, to the last lesson of Chapter 2. Lesson 2.4, Modeling with Quadratic Functions. So in this lesson, we're going to be given some data, usually in the form of a table, and we're going to be asked to see if it can be modeled by a quadratic function or not. And once we determine it can be, then we're going to learn how exactly to go about doing that. So the first problem that we're given, actually before the first problem, we're given a little bit of an introduction to this whole idea of modeling data. So we're given a table, okay, and in that table we're going to have our x values and our y values, also known as f of x. Doesn't matter what you write there. And then we're going to be given several points, and we're going to have -3 as an x value, -2, -1, 0, 1, 2, and 3. And then the f of x values for these corresponding x values, those are going to be 9, 4, 1, 0, 1, 4, 9. Now some of you guys might already know, just by looking at this data at these points, what this function is. This function at 0 has a value of 0. At 1 has a value of 1. At 2 has a value of 4. At 3 has a value of 9. At -1 also has a value at 1. At -2 has a value of 4. And at -3 has a value of 9. So if you guessed it correctly, this is just the parent quadratic function. This is our old friend f of x equals x squared. But let's say you didn't remember that and you need to start from scratch and you're given these values and you're like, okay, can I use a quadratic function to model this data? Well, the first thing is to look at the x values. -3, -2, -1, 0, 1, 2, and 3. They must be equally spaced. So if you take a look, -3 plus 1 is -2, -2 plus 1 is -1, -1 plus 1 is 0, 0 plus 1 is 1, 1 plus 1 is 2, and 2 plus 1 is 3. Now they don't need to be equally spaced by 1. They could be, you know, adding 2 to each one, or adding 3, or adding 5, or adding 10. As long as the spacing is equal, we're able to work with that. So that's the first thing you need to check, is that your x values are equally spaced. Okay? Then we're going to do what is called finding the first differences. And the first differences are found. We're going to now ignore the x values for a while. We're going to work with the y values. We're going to do 4 minus 9. 4 minus 9 is -5. We're going to do 1 minus 4. 1 minus 4 is -3. We're going to do 0 minus 1. 0 minus 1 is -1. We're going to do 1 minus 0. That's +1. We're going to do 4 minus 1. That's going to give me 3. And 9 minus 4. That's going to give me 5. So now we look at this data and, well, it really doesn't do much for us, anything. It's all of the numbers are different. None of them are the same. We do notice that you have a 1, a -1, a 3, a -3, a 5, a -5. But honestly, what you're looking for is to see if these first differences are constant. if this was the same value over and over again, we'd be able to use a linear function to model it. So linear functions can be used when first differences are a constant number. So once again, if instead of these numbers, every time we subtracted, let's say we got 2, 2, 2, 2, 2, and 2, we would say that that was a linear function, and we could model it with a linear, that it represents a linear function, and we could model it with a linear function. But that's not what happened here, and that's okay. So we look at the first differences, and for us right now, it does nothing for us. You can't use a line. This is definitely not linear. So we're going to do what's called taking the second difference, or the second differences, and then we're going to do -3 minus -5. Okay, now make sure you get that. -3 minus -5. This is going to become a plus. So -3 plus 5, that's going to be +2. Then we're going to do -1 minus -3. So -1 minus -3. Again, you're going to get +2. Then we're going to do 1 minus -1. 1 minus -1. So once again, we're going to get 2. And then 3 minus 1, that's 2. 5 minus 3, that's 2. Now if you notice, the second differences are the same number. It's a constant number. They're 2 always, right? So that's telling us that this function is quadratic, and we can use a quadratic function to model the data. Since the second differences are a constant number, the data can be modeled using a quadratic function. Okay, so this is basically a test to see whether our data can or cannot be modeled using a quadratic. Remember, if you get the same numbers in the first differences, you can use a linear function to model it, which really we're not doing in this lesson. We're focusing on the quadratic, but just know that that is a thing. And then if the second differences are constant and they're all the same, then you can use a quadratic function to model it. Okay? So with that being said, let's go ahead and look at our first example. Example number 1. Okay, example number 1 has to do with a problem where there is a, well, actually, let me just go ahead and read the problem to you, okay? And this, again, is coming straight from the notes. I do have pictures of the notes in Schoology. Let me see if I can put this up here. Hold on. Let's see if I can switch. I'm just I'm a little worried about switching screens on you guys, so I'm not going to do that. But this is example 1, and it is from chapter 2. It's on page 88, and I'm just going to read it to you. NASA can create a weightless environment by flying a plane in parabolic paths. The table shows the heights, h of t, in feet of a plane, t seconds after starting the flight path. After about 20.8 seconds, passengers begin to experience a weightless environment. Write and evaluate a function to approximate the height at which this occurs. All right, that's a whole lot of stuff. But let's kind of draw this out. So right now, I'm going to apologize for my drawing. I always got C's in art, so there you go. This is my plane. All right, oh, there it is. There's a little cockpit right there. All right, and there's the propulsion for the plane. So we have this plane, okay? And what they're doing is they're using the plane, and this was originally done many, many years ago with NASA to prepare their astronauts to be in a weightless environment for when they would go up into space. You obviously couldn't send them up a million times before because they had to go there for the first time. You didn't really want them to experience weightlessness for the very first time when they were actually in outer space. So you would put them in airplanes and you would fly these planes in parabolic functions. You would take the plane up to a certain height and then bring it down, and repeating it over and over again. Very quickly, what it does is it produces the effect of being weightless. Obviously, you're not going to really be weightless, but you're going to feel like you're floating. And if you guys are interested, and I showed everybody in class, give me just a second, there is a site where you can pay some money to go on one of these weightless plane flights. And again, I'm not selling these flights or anything, but just so you see it, it's called Zero G, and if you go to gozerog.com, you're going to actually see what I'm talking about. And the people are kind of like floating inside the plane because they go through all of these parabolas very, very, very quickly, and it imitates or it duplicates the effect of being in a weightless environment, of being in outer space. So, like I said, back in the day, it was done just for astronauts, but now people that have a lot of money go ahead and take these flights. If you look down at the prices, some of these flights are like $9,000. That's the cheap one, and then you can get one for like $260,000. They give you like an exclusive flight. So that's what this plane does, is it goes in parabolas, and it keeps going around and around in parabolas very quickly, and when it reaches a certain after a certain time and at a certain height in that parabola, the person is going to start floating. They're going to feel like they're weightless. Okay? So here's our problem. We're given a table, and again, this table is in your book. Again, on page 88, much nicer, much nicer than what I'm doing here. This is very rough here. You're going to have time, which is measured in seconds, and we're going to use little t. And our height is the dependent variable. It depends on time, and that's going to be your h of t. So at time 0, the plane is at 21,000 feet. Again, height is given in feet, so let me just put that there. Time is in seconds. At 10 seconds, the plane is going to be at 26,900 feet. So it's going up pretty fast in 10 seconds. You're going to feel that. At 20 seconds, the plane is at 30,600. At 30 seconds, you're going to be at 32,100. At 40 seconds, you're going to be at 31,400. And I always forget for that last little space. At 50 seconds, you're going to be at 28,500. So before we start, let's look at the data and see what this tells us. At time 0, that means this is before the plane starts to do the parabola. Okay? So apparently, here's the ground down here. Again, do not make fun of my artwork. All right? We've got these giant trees that almost reach the plane. I get it. But at time 0, the plane is just flying at a constant height here of 21,000 feet. Okay? Let's put that right. 21,000 feet. All right, so it's just gliding along. It's kind of like when you go on a plane and you reach cruising altitude. All right, this is cruising at 21,000 feet. And then suddenly you start the timer. Let's say you have a timer and you start going into the parabola. That's when the fun begins. You start going up really fast and down and then up and down. And that's pretty much when I throw up, because that would make me very sick. But a lot of people will begin to get weightless, and that's going to be pretty cool, I guess, if you're into that. So you're starting at 21,000 feet. That's your cruising altitude. If you notice, within 10 seconds of the plane starting its journey on the parabola, it's going to shoot up in 10 seconds. It's going to go up by, gosh, almost 6,000 feet, which I don't know about you, but that sounds like a lot. And then after 10 more seconds, it'll go up another bunch of feet, and so on. If you look at the table, you see that it's increasing from 0 to 10, and then it's increasing from 10 to 20 seconds, and then it's still increasing up till 30 seconds. But then something happens after 30 seconds, and the height starts coming down. So what we can assume, again, is that this is going up. Let's say this is at 0 here. Here we're at 10, 20, 30, maybe 30 is closer to here somewhere. And then we'll start coming down, 40, 50, right? Ignore that. We're just kind of showing what's going on. Now, this does not mean that this is the vertex. No, we don't know that for a fact. In fact, we would have to figure it out a different way. But we do know that between 30 seconds and 40 seconds, the plane starts coming down. Okay? So the trajectory is starting to go down. We do know that because the height starts decreasing. So that's all we can tell right now from that data. All right, so the problem is asking us, all right, with this data, can this be modeled as a quadratic function? So once again, we're going to do that process that we did right up here, but we're going to do it with this data, okay? So we're going to need to find the first differences, and we're going to need to find the second differences. And again, we're dealing strictly with these values here, with the function's values, or the y values, if you want to call those. So we have 21,000, we have 26,900, we have 30,600, we have 32, and I'm going to run out of space. We have 31,400, and over here we have 28,500. So we're going to do the first difference. We're going to take this and subtract that from it. And if you do 26,900 minus 21,000, you're going to get 5,900. Then we're going to do this minus this. So 30,600 minus 26,900, that's going to give us 3,700. Then we're going to do this one minus this one, and that's going to give us 1,500. Then we're going to do this minus this. That's going to give us negative 700. And finally, you're going to do this guy minus that guy, and that's going to be negative 2,900. Now by looking at these, we can see these are all very different numbers. So, and these are your first differences. So obviously, from what we see here, a linear function would not be able to model this. So that's what we learned from that part. So now we're going to do the second difference to see if in fact a quadratic function may be able to model it. So we're going to subtract this from this, and that's going to give me negative 2200. This from this, negative 2200. This from this, negative 2200. And this from this, also negative 2200. So, yep, we see that the second differences, which is what we were hoping for, the second differences are all constant. So that means that yes, this can be modeled. So we have that answer. Now we need to go ahead and do the modeling. Okay? All right. So let's move on. So let's go over here. Now we're going to put this in standard form. Okay? The quadratic, standard quadratic form. It's going to be h of t because that's what they were calling it, right? Height, h of t equals, that's going to be a, instead of x we're using t for time, plus b t plus c. Now from what we know about the standard form of a quadratic, this c is our y-intercept. It's the value of the function when, in this case, t is equal to 0. So if we look at our table of values, when time is 0, the function is at 21,000 feet, right? It's flying at that cruising altitude right there of 21,000. So we can go ahead and put that in. So my h of t equals a t squared plus b t plus 21,000. Okay? All right. Now we need to figure out what this a and what this b are in order to create our function, right? In order to create our quadratic function. So what we're going to do is we're going to go back to the table and we're going to pick 2 points, any 2 points you like, and we're going to create a system of equations, and we're going to use elimination to solve for a, and then to solve for b, or to solve for b and then solve for a. And so I'm going back to the table and I'm going to pick 2 points. You can pick whichever ones you like. I'm going to stick to the smallest values because generally they're easier to manipulate. The math is easier. So I'm going to use the point 10 comma 26,900 and 20 comma 30,600. So the 2 points are going to be 10 comma 26,900 and 20 comma 30,600. Now remember what these points represent. They represent t and h of t. So let's go back here. This is time and this is h of t, which is the height of the plane. So t, h of t. So for this first one, I'm going to substitute whatever my h of t is here, which is 26,900, for h of t, and I'm going to rewrite this whole thing. So instead of h of t, I'm going to put 26,900 equals, I don't know what a is, but I know that t is 10. So this is a times 10 squared. Again, I don't know what b is, but I know t is 10, and I've got 21,000. All right, so let's simplify this a little bit more. 26,900 equals 10 squared is 100. So this is 100A plus 10B plus 21,000. Simplify it a little bit more. Let's get rid of this 21,000 by subtracting 21,000 from both sides of our equation. Okay? So when we do that, we are going to get over here 5,900 equals 100A plus 10B. And one last thing I'm going to do is I'm going to flip these around because it's just nicer to look at when your variables are on the left and your constant is on the right. And this is what we're going to call equation number 1. Let's make it a different color, or maybe like highlight it somehow. All right, so that's this guy right there. 100A plus 10B equals 5,900. That's the first one. That's coming from my first point. Now let's do point number 2. So for point number 2, which is this guy, we're going to do exactly the same thing. Instead of h of t, we're going to put 30,600 equals. We don't know what a is, but we know that t squared is going to be 20 squared. So that's 20 squared plus b. We don't know what b is, but we know t is 20. And plus the 21,000. Okay? Simplify this a little bit. This is 30,600 equals 20 squared is 400a plus 20b plus 21,000. Once again, we're going to subtract 21,000 from both sides because we want to simplify this. So if I subtract 21,000 from 30,600, I'm going to get 9,600 equals 400a plus 20b. And the last thing is I'm going to flip these around just to make it look nicer. 9,600. And this will be equation number 2. All right. So those are our 2 equations for our system of equations. All right. So now we're going to put the 2 equations together and we're going to see what we can do. So equation number 1 is 100a plus 10b equals 5,900. Equation number 2 is 400a plus 20b equals 9,600. And now is when we do the process of elimination to get rid of either A or B. And this is one where you just have to look and kind of see, well, what's the easiest thing to get rid of? From what I'm seeing right here, the 10B and the 20B, if I multiplied everything in the top one by -2, means I have to multiply -2 times this, -2 times this, -2 times that, I should be able to cancel out my b's. So let's go ahead and do that. So my first equation up at the top is going to now become negative 200a minus 20b equals negative 11,800. This guy stays the same because something really cool is going to happen now. And the cool thing is that when I add these terms, these guys are going to go away. So negative 200a plus 400a, that's 200a. Negative 20b plus 20b, that goes to 0, which is exactly what you want. You want to get rid of one of those variables. And then 11,800 plus 9,600, that's going to be negative 2,200. We divide both sides by 200. That cancels. A is equal to negative 11. Okay, we're moving on. We've got A. That is a big deal. So that's important. Next thing we need to figure out is, well, what is B? Well, to figure out what is B, you can go back to one of these two original equations, whichever one makes you happy, and you're going to plug in negative 11 for A, and then you're going to figure out what B is. So I'm going to take this guy right here, because again, the numbers are smaller and it just looks easier. So I've got 100, but instead of A, I'm going to put in a negative 11 plus 10B equals 5,900. This is going to give me negative 1100 plus 10B equals 5,900. I'm going to add 1100 to both sides, and I'm going to get 10B equals 7,000. Divide both sides by 10, and B is 700. So, okay, we're in business. We know what A is. We know what B is. So now we can go way, 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 way back to this original guy and plug in A and plug in B. So once again, A was negative 11. So let's rewrite this. H of t equals negative 11t squared plus B was 700t plus 21,000. So we've got our quadratic function. This is huge, guys. This is huge. We're almost there. But we haven't answered the question yet. Okay? A question, if you remember, and you probably forgot by now because I'm going to read it again. The question said NASA can create a weightless environment by flying a plane in parabolic paths. And that's what we did here, the parabolic paths. The table shows the heights and the feet of the plane t seconds after starting. After about, here's where we're going. After about 20.8 seconds, passengers begin to experience a weightless environment. Write and evaluate the function to approximate the height. So we want to know what is the height when people are floating in the plane. So obviously if we have our equation and our time is 20.8, all we have to do is for t plug in 20.8, and that's going to tell us how high the plane is when people are feeling that feeling of weightlessness. Okay? So let's do that and then we're done. So we've got negative 11 times 20.8 squared plus 700 times 20.8 plus 21,000. Now obviously use a calculator, guys. Don't do this by hand. This is silly. So go ahead, make sure you do your order of operations. So make sure you do 20.8 squared first, then multiply by negative 11. You're going to get minus 4759.04. Then do 700 times 20.8. You're going to get 14,560. And then add your, oops, I'm going to lose, I don't have enough space. And then add your 21,000. So we're going to take negative 4,759.04 plus 14,560 plus 21,000, and you should get a grand total of 30,800.96, and this is feet. That's how high the plane is off the ground. And that, guys, is actually your answer right there. So at 20.8 seconds, when people are on this plane, at 20.8 seconds, so somewhere, I'm going to say, because it starts going down after 30, so somewhere around here, the plane is going to be at 30,800.96 feet, and people are going to be floating. Pretty cool, right? Again, if you have not looked at the website that I gave you, check it out so you can see. Go to the site right here and check out what it is to feel like you're in that weightless environment, which I think is pretty cool. Definitely not for me, but for those adventurous types, I can see that being pretty cool. For me, I would probably have a heart attack and die, so that would not be a good thing. All right, so the answer, the final answer, and I'll write it down here, at 30,800, we can just round it to just the nearest whole number, feet, your passengers will begin to experience weightlessness. Okay? And that was example 1. I promise example 2 is much shorter. All right. So we're going to do example 2, and example 2 will be the last one. So, oh, did I spell that wrong? Weightlessness. Okay. All right. Example 2. Example 2 has absolutely nothing to do with flying. Yay! It is actually having to do with a concert, and well, let me read it. The table shows the estimated profits in dollars for a concert when the charge is X dollars per ticket. Write and evaluate a function to determine the maximum profit. So apparently there's somebody who's doing a concert, and they want to figure out what is the maximum price they can charge for a ticket where people will still buy the ticket. Let's put it this way. Just because, like for example, if you wanted to make the most amount of money by hosting an event, you would charge the most you could per ticket. But there comes a point where if you charge too much for a ticket, people are not going to go to your event, and you're going to actually start losing money. So what you're looking for is that sweet spot where people will pay the most that they're going to pay, but they're not going to be so turned off by the price that they won't go to the event. Yeah? And companies do that all the time. They'll figure out a price point where consumers will go and pay this much, but if you make it any more, they're just not going to do it. For example, I was looking the other day at an Apple Watch for my daughter for Christmas, and they're always $399 every year. Doesn't matter. It's just a constant price, because the people at Apple, they've realized that if they make it $400, that's not good. It's still under $400, so they're going to do $399, and that's the spot where more people are going to buy it, and they can get away with it. Obviously, they could charge $2,000 for an Apple Watch, but how many people would be able to buy that? Okay, so you're looking for that perfect price where you're going to make the maximum amount of profit, and people are still going to either buy your product or, in this case, go to your concert. Okay, so here's the data from the concert. If we give the tickets away, if we don't charge anything for this concert, you're going to be $1,000 in debt. And you're probably saying, well, why? Well, when you set up a venue, right, you're going to do some sort of an event, you've got to pay for the venue, right? That's money that you got to give. You got to pay for the lights, right? You got to pay for the AC because you don't want people, passing out because it's really hot. Maybe you need security, right? So you have this called overhead whenever you do some kind of an event like this. So obviously it costs $1,000 just to turn on the lights, get the air conditioning going, get your security in place, whatever it is, or rent your venue. So that's why if you gave the tickets away, which I don't know why you would do that, but if you gave them away, you didn't charge anything, you would be $1,000 in debt. Okay? This X represents the price of a ticket, price per ticket, and this is your profit. How much are you going to make? All right? So obviously, let's not give the tickets away. Let's charge them at $3 each. Let's see what we do. The table tells us that if you charge $3 per ticket, you're going to come back with $4,100 in profit. Okay. If you charge $6 per ticket, let's make it a little more expensive because $3 is pretty cheap. If you charge $6, will people still go? Yeah. You're going to make $7,400 profit. Okay. If you charge $9 per ticket, are people still going to go, or is it going to be too expensive? Well, it looks like they're still going to go. You're going to get $8,900 profit. Again, I always am short by one of these. Okay. If you charge $12 per ticket, you're going to make $8,600 in profit. And if you charge $15 per ticket, you're going to make $6,500 in profit. So right there, you're like, wait a minute. It looks like the most I'm going to make is $8,900, because then it starts going down again. It starts decreasing. So something happened between $9 per ticket and $10 per ticket. You hit your sweet spot. So maybe it's $10, maybe it's $11, maybe it's $10.50 or whatever. There's a value between 9 and 12 where you reach your maximum, right? And after that, you start actually making less money, even though you're charging more per ticket. All right, so that's the scenario. Let's go ahead and do first differences. So we're going to subtract this from this, this from this, this from this, this from this, and this from this. And this is just to see if we can use a quadratic function to model this. So this is going to give me 5,100. This is 3,300, 1,500, minus 300, and minus 21. This is first differences. Again, these are not the same numbers, so obviously this is not a linear function. This is not a linear relationship. So now we're going to do second differences to see if we can, in fact, use a quadratic function. So this minus this, this minus this, this minus this, and this minus this. This is going to give me negative 1,800, negative 1,800, negative 1,800, and negative 1,800. So yeah, we're good. This can definitely be modeled, yay, with a quadratic. All right? Okay, next step. We mentioned that if you gave the tickets away, if you didn't charge anything, you would be $1,000 under, right? You'd be in the negative or in the red. This is our y-intercept. When x is 0, y is negative 1,000. So we have a y-intercept at negative 1,000. And we're going to use that to create our equation. So our equation is, and I'm using y here instead of f of x because they used y. It doesn't matter. Ax squared plus bx, and then don't forget the minus 1,000. Okay? So this is going to be our base function. We're going to need to figure out what a is, and we're going to need to figure out what b is. And just like before with the plane and the weightlessness thing, we're going to need to pick 2 points from the data. Again, I'm going to pick the smaller numbers because they are easier to work with. So my first point is going to be at 3, 4,100. And my second one is, I'll put it down here, at 6, 7,400. Okay? So remember, this is your x, this is your y, this is your x, this is your y. So I'm going to rewrite this with these values. So instead of y, I'm going to put 4100. We don't know what a is, but we know x is 3, so this is 3 squared. We don't know what b is, but we know x is 3. So this is 4100 equals 9a plus 3b minus 1000. We're going to add 1000 to both sides, right? So this is going to be 5100 equals 9a plus 3b. And I'm going to flip it around just so it looks nice. It's just easier to read, I think. We're just used to seeing it this way. Remember, it is equal, so you can switch what's on the left with what's on the right. And this will be our first equation right there. This is the one we're going to use for that system of equations, one of them. 9a plus 3b equals 5100. Now we're going to do the second point. So instead of y, we're going to do 7400. Again, we don't know what a is, but we know x is 6, so that's 6 squared. We don't know what b is, but we know x is 6 minus 1000. So this is 7400 equals 36a plus 6b minus 1000. Again, we're going to add 1000 to both sides, so we have 8400 equals 36a plus 6b. And the last step is to flip it around just to make it look pretty. 36a plus 6b equals 8400. And that's equation number 2. Boom, 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 boom. All right. Now, we're going to put these together. So we have the first equation, 9a plus 3b equals 5100. And we have 36a plus 6b equals 8400. Once again, we have to look, and we're using the process of elimination. What can we get rid of easily? And what I'm looking at is this b statement. If I multiply everything up in the top by a -2, now remember that means multiplying this, this, and this by -2, I'm going to be able to cancel out those b's. So let's do that. That's going to be -18a minus 6b equals -10,200. And then I'm just copying the second equation. And once again, -18 plus 36, that's going to give me positive 18a. That goes to 0, which is what I want to see. And this is going to give me negative 1800. Divide both sides by 18. And a is negative 100. Oops, so we're almost there. All right, in order to find what b is, you need to go back to one of these two and plug it in. Again, I'm going to pick the one that has smaller numbers. So 9 times, instead of a, negative 100 plus 3b equals 5100. And this is going to give me negative 900 plus 3b equals 5100. I'm going to add 900 to both sides. 3b is 6,000. Divide both sides by 3. B is 2,000. All right. So now, I know, you're tired. We can go back to that original one right up here and plug in a and b. So I'm just going to rewrite it really quickly. It looked like this: ax squared plus bx minus 1,000. But now we know that a is negative 100, b is 2,000, and we just put in the rest. So we have our equation. Great. But that is not the answer to my question. One more time, the question was, write the function to determine the maximum profit. Now your spidey senses should be tingling, because when we say maximum and minimum, we're looking at a vertex, right? And that's exactly what we're doing. We want to find the vertex of this equation. Before we do that, we need to find its axis of symmetry. So the axis of symmetry, if you remember correctly, is going to be x equals negative b over 2 times a. That's going to be negative 2,000 over negative 200. And that's going to give us positive 10. Okay? So the maximum profit is when x is 10. Now if you remember, x represents the price tickets. So when x is 10, which makes sense, it's between 9 and 12, that's where your vertex is, or your maximum is. So apparently once the tickets are over $10, people stop going to your concert. Not as many people go. So we have 10 for our vertex. We have 10 comma. Now 10 stands for the price, so it's really $10. And now we are looking for the profit. And in order to find the profit, we need to take the 10 and plug it back in here. So y equals negative 100, and my x is 10, so this is 10 squared, plus 2,000 times 10 minus 1,000. Okay? Again, remember to do exponents and parentheses first. So this is 100 times negative 100. That's negative 10,000. Plus, this is 2,000 times 10. That's 20,000 minus 1,000. And this is going to give us $9,000. And this is your profit. And that, guys, profit, sorry, that is your final answer. $9,000 in profit. So the most you can charge for a ticket is $10. Guys, I know this was a long one. I apologize, but hopefully the video helps. Hopefully the video helps. If you have any questions, come see me in class. Chances are, and I'm leaning towards not putting one of these on the chapter test. So I just want to expose you to them. I want you to practice them on big ideas. But I'm 99% sure that I'm not going to put one on the chapter 2 test. Okay? So just be aware of it, know how they work, and practice them and ask me any questions. See you next time. Bye.